Okay, all right. So, welcome, and we can start with this new topic here. This is something which is essential for all NMR experiments. In some parts, we have discussed it already in different pieces. So, this has to do with what is known as phase cycling and gradient enhanced NMR. So, what is phase cycling? Let us see here. What do you want to do here is systematically vary the phases of RF pulses and receiver in a pulse sequence. We have seen some examples of this in when we discuss the particular experiments like NOESY, double quantum filtered COSY. We will refer to that again today also. And the idea is to compensate for imperfections, number one, that is different objectives are there, cancel artifacts, select for the desired signals only. The receiver phase has to match the phase of the desired signal. This is how you select a particular signal which you want. As you have seen in the previous lectures, that we create all sorts of signals, Z magnetization, single quantum coherences, double quantum coherences. All of these are created by during the pulse sequence. But you want to select one of those, and then you have to adjust the phases of the pulses and the phases of the receiver to select what you want. Okay, this is the general outline of this phase cycling. Okay, a very common example, very simple example is to see what is the meaning of the receiver phase and the pulse phase together. So if you have the pulse and the receiver along both axes, this is what is indicated. So we are looking at the transverse plane. So after the pulse is applied, the magnetization lies in the transverse plane. So if you have a X pulse, then the receiver is along the minus Y axis. We call it as the receiver X, the zero phase or whatever. How the receiver phase is made to follow the phase of the magnetization, because it always has to follow the phase of the magnetization. Then only you will get a signal. Otherwise, you won't get the signal. So therefore, if you apply a Y pulse, the magnetization lies along the Y axis. Then you will have to put the receiver also along the Y axis. So minus X, minus Y, minus Y. So this is how you have to see the dot indicates the receiver. Okay. So pulse and then the receiver where the magnetization is and where the pulse is. So therefore, we will have to see where are the receivers and the phases the pulse is applied. So cancels imbalances between X and Y channel of the receiver. See, you collect X magnetization and Y magnetization. Ideally, magnetization when it is rotated from the Z axis onto the along the X axis or the Y axis, the total magnetization has to be the same. And that means the receiver has to be identical in both cases. Whether you put the receiver along the Y axis or you put it along the X axis, it has to be identical. If there are imperfections in those, then you try to cancel some of these out by doing this cycling. You X minus X, Y minus Y. When you do these, imperfections of the two will get cancelled out. So that is known as that kind of a phase cycling is known as cyclops. Cancels imbalances between X and Y channel of the receiver system and eliminates the quadrature spike. Of course, quadrature spike has not been talked about probably. I will talk about it as we go along a little bit. So X, Y minus X minus are usually referred to as 0, 1, 2, 3 or 0, 90, 180, 270. Now, sometimes you may wonder what is the meaning of X or Y axis in the three-dimensional space here. Where do you fix the X axis? Where do you fix the Y axis? So what is the meaning of X, Y minus X minus Y? So this is basically the relationship between the magnetization and the receiver. The 90-degree phase difference. There is always a 90-degree phase. If the phase is the same, then of course we say same 0, 0. But if the phase is 90 degrees apart, then we say, okay, the signal phase and the receiver phase are 90 degrees apart, then we say the receiver phase is 90 degree. And if it is to 180 degrees apart phase, then we say it is 180 degrees or we say minus X. So if the signal is along the X, then we say it is 0. And if the receiver is 90 degrees apart, phase is 90 degrees apart, then it is Y. So what is the meaning phase 90 degrees apart? See, whatever radio frequency you apply to a transmitter, you apply radio frequency to the transmitter, which is a sine wave, right? So the sine wave or the cosine wave you apply. So it has a certain phase. Now the same signal, same RF is applied the fed to the receiver also. It is applied to the receiver also. So if the two things are coherent, then we say they are in phase. Both have 0, 0 phase. If the transmitter starts with a particular phase here, then the signal RF that is generated. If the receiver is 90 degrees out of phase with respect to that, then we say it is along the y-axis. If I call this as the x-axis, then the 90 degrees out of phase is called as the y-axis. If it is 180 degrees out of phase, then we say the minus x. So this is the relationship between the transmitter and the receiver. So typically, instead of saying xy minus x minus y, sometimes we also write it as 0, 1, 2, 3 or 0, 90, 180, 270, because this goes in steps of 90 degrees. It is not necessary that it should go in steps of 90 degrees only. You can also have phase shifts of 20 degrees, 30 degrees, 40 degrees and things like that. Those are the phase shifts you can use specifically to particular receiver. Such things are used in very special experiments, but by and large, to cancel the artifacts and things like that, all the imperfections in the two channels, if the two channels are not equal, to cancel out the differences between these two, then you by and large use 0, 90, 180, 270, xy minus x minus y. That is what we use. So the receiver phase follows the signal phase, okay, phase of the magnetization. This is the illustrate how the receiver phase made to follow the phase of the magnetization. Okay, so you keep that in mind. Okay, that is basically the phase cycling, principle of the phase cycling. Now where do these things occur and where are these required? 180-degree pulses. We call 180-degree pulses the refocusing pulses, right? They remove the effects of an imperfect refocusing pulse. So what does that mean? So when we say refocusing, here it is indicated here. So if I apply 90x pulse, it is coming along the minus y-axis. Okay. So let us say for a period tau, what happens? This magnetization has moved over here during the period tau. Now when I apply the 90 x pulse, here let us say, then where it will go? If I apply 180-degree pulse, the magnetization will move here. Okay. If it is perfect 180 degree, it will come into the same plane as that. It will come exactly on that. If I apply it along the y-axis, then it will move from here to here. It will come here. So these are perfect. That means they will remain in the same plane. It will remain in the same plane. But if they are not in the same plane, what happens? The amplitude of this component, there will be components along the x and the y component. There will be some component will be there along the y, some component will be there along the x. Now these will have to be cancelled out. The other things which are there have to be cancelled because the receiver has to be adjusted to only one of those. So when you adjust the receiver to one of those, other one will have to be cancelled out. So therefore, what you do is you cycle the phase and cycle the receiver of the phase of the 180-degree pulse and phase of the receiver. This is also true for general inversion. Suppose your magnetization, I've drawn the transverse plane here, but you can also do that when your magnetization is along the z-axis here. If you apply 180-degree pulse, let us say here, where the magnetization should go, it is supposed to go exactly here. If it is perfect 180-degree, it should go there. But if it is not, then what will happen is, it will come somewhere here. If it is not rotated by 180, it is, let us say it is rotated by 170 degree. This is the imperfection in the pulse. It can be a wrong setting. You have not set the 180-degree pulse properly. It can happen that way. Then it will come here. In that case, what will happen? There will be a certain component along this negative z-axis and a component in the transverse plane. You don't want this component in the transverse plane. Okay, so what you are trying to measure is the component in the z-axis, the 180 degree that has come. It will be slightly reduced in intensity, but nonetheless, this component which has come here, suppose it is along the made a rotation along this, the magnetization has rotated from here to here. If I applied a pulse here, now it has generated a component along this axis here, in the positive this axis here. Now I do a second experiment where I apply the pulse along here. The magnetization rotates here. Okay, so it will come up till here. So it will come here. So therefore, it will now generate a component. This component remains the same because it is also 170 degree, but it will have a component here. Okay. and the transverse plane. This component will be exactly equal and opposite to the component which is generated on the top here. Therefore, when you add the two, that thing gets cancelled out. Whatever is remaining on the transverse plane, that will get cancelled out. So this is how you cancel out the imperfections or the inaccuracies in your pulses. These are shown with the Z and magnetization. The same thing applies here as well. To the transverse plane also the same thing applies. If the 180 pulse is not proper, there will be certain component remaining along the Z axis, and that Z axis component you cancel out by cycling the phase through as y minus y and x minus x in that manner. Okay, so this is for the refocusing pulses or the inversion pulses. This is also inversion pulse. In the transverse plane, when you're talking about, it is a refocusing pulse. If it is for the Z axis, that is an inversion pulse. Okay, what are the applications of this? I showed you the Cyclops, which is a standard thing in all 1Ds we use it, Cyclops, to cancel out all the imperfections in the pulses. Now in two-dimensional experiments, this becomes even more important. Let's take, for example, the Cozy experiment. The Cozy experiment is in the simple two-pulse experiment here. We have seen when you apply the first 90-degree pulse, the magnetization comes on the transverse plane. Okay, when I apply the first 90-degree pulse, the magnetization comes here after the first 90. Okay, we are in the magnetization is precessing in the transverse plane, and we are manipulating the evolution of the magnetization and calculating the cross peaks and diagonal peaks and things like that. That is during the T1 period. But what happens during the T1 period? There is also relaxation. There is also relaxation. Some component of the magnetization recovers back to the Z-axis. Okay, which some component of the magnetization recovers to the Z-axis. Now this magnetization loses the frequency label. So during the T1 time, it has no frequency label because it's along the Z-axis. So at the end of this, we have a transverse magnetization which we are going to exploit for creating the diagonal and the cross peaks. But there is also Z magnetization which is created here that will stay here, Z magnetization. When you apply the second 90-degree pulse, it will appear along the T2 axis. It will also produce magnetization in the transverse plane, and you will evolve it also. So where will these peaks appear in the two-dimensional spectrum? These peaks will appear at zero frequency in the F1 dimension because it has not frequency label. It has relaxed in the T1 period. It has gone onto the Z axis. Therefore, it has no frequency label. So therefore, it is at zero frequency. So at zero frequency in the F1 dimension, you will get a signal along in the T2 dimension, and that will produce your peaks. And many times these are very huge. These are called as axial peaks. These are huge axial peaks. Because it depends on the relaxation, how much relaxation happens. You remember the T1 is incremented systematically. You go from 0 to let us say some 50, 60 milliseconds. That's quite a lot of time. So during all these periods, it is relaxing at different this thing, but the frequency level is not there. So it is accumulating over time, and then you will collect that signal as on the positive Z axis. Now, how to eliminate this? So what we will have to do is, at one point, you put it along the positive Z axis by this pulse. If you put it, suppose it's relaxed here. Now, the one pulse if I apply to bring that magnetization here, by applying a pulse, let us say along this axis. Okay, this magnetization comes here. Now, we have to do another experiment where I apply the pulse. Apply the pulse along this, so that magnetization comes here. That magnetization comes along this axis here, right? So this magnetization, initially it rotated from here to here. Now in this experiment, it rotated from here to here. So this is one experiment and this is another experiment. Now we add the two. Therefore, whatever had recovered here, that gets cancelled out. So that is called as the suppression of the axial peaks. See, that is what is indicated here. The phase of the first pulse, P1, is kept 0, 0 both the times. And the second pulse, once it is applied along x-axis, second time it is applied along the minus x-axis. So whatever magnetization had recovered during the T1 period onto the z-axis, so will be along the plus y or the minus y on in the transverse plane. And when we add those two signals in the receiver, so they will get cancelled out. Therefore, that will not contribute to your observed signal, and you will only get clean diagonal peaks and the cross peaks. The same strategy is applied for all other experiments. I've shown you for COSY, but the same thing is applied for all other experiments, because sometimes these peaks are very, very huge and it can block all of your cross peaks and the information in the spectrum. Okay, so this I have already shown you earlier. Once you want to select particular pathways of magnetization. So pathways of magnetization is the receiver has to follow your signal. The receiver has to go in phase with the signal. You pick out those components of the magnetization which you require. And you do that by adjusting your receiver phase so that that particular signal is picked up. As we have seen in the NOESY spectrum, we cycle this phase of these pulses as xy minus x minus y, and we added all these things in the receiver, plus, 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 plus. We have explained this earlier. In the case of double quantum filtered COSY, we did the set of 4 experiments, 4 scans, and the phase of this pulse was made xy minus x minus y, and we changed the receiver plus, minus, plus, minus. We carried out detailed density operator calculations here, right, to show how this is picking up double quantum filtered signals, how this one is picking up the Z magnetization. Here the Z magnetization is picked up. That is what is required for the NOESY experiment. Z magnetization is here. At this point we are picking up Z magnetization, and the NOE happens after that, from during this period tau m. This is your tau m period. Okay. In the double quantum filtered COSY, you are getting the double quantum signal here. You are selecting the double quantum filtered COSY of all the magnetization components that have been created through this T1 evolution, and then after that you convert this into the observable magnetization by this 90x pulse to detect it. So therefore, the selection of the different signals is manipulated, is achieved by changing the receiver phase and the phase of the pulses. Okay, this example we have considered earlier. Okay. Now, before we go further, I will have to use some definitions here. We have to introduce a term called coherence order. This becomes particularly important. We can use it in the case of normal phase cycling schemes as well, but this becomes even more important when we talk about gradient enhanced NMR. So here have to introduce certain things for a term called as coherence order. So there, zero quantum signal is called as coherence order 0. Single quantum coherence is called as with the coherence order +1 and -1. +1 stands for a p-type and -1 is refers to the n-type. These are the nomenclatures. And double quantum will have p is equal to +2 and -2. Triple quantum will have p +3, -3, and so on. So this number is called as the coherence order. And this is important because the phase that the signal acquires afterwards will depend upon what is the coherence order. Okay, so let's try and understand this. Now we turn to the pulse field gradients. Okay, what are these pulse field gradients? So pulse field gradients are, you have the main magnetization here. Okay, you have the magnetization main B0 field, and on top, maybe it's there in the next slide. Okay. Yes, so here it is. Okay. So typically you have a sample like this. You have a sample, you have the tube and your solution which is like this, and you record a spectrum of this, you will get one line which is the particular frequency. And we have not applied any gradient here. There is no gradient. What does the gradient do? So when you apply the 90-degree pulse, you have free precession for the period t, and free precession is indicated by this movement of this transverse magnetization. And when you Fourier transform it, you will get a signal which is this one frequency here, assuming that there is only one frequency for the moment. There can be more. Whatever are there, they will all appear there. Now, when you do a gradient means in addition to this main field, the main field which is present here, B0 field, we apply another field. This is the other field which changes with distance, with the distance along this. That's why it's called as the gradient. Okay, so this is the z-axis, this is the z-axis, and it has a slope, and we say the gradient if is zz. So at any point here, the field, additional field which is applied is given by gamma gz z. Z is a coordinate. Z is a coordinate along this. Zz is the gradient. That is the slope. Okay, this is the, you have the slope here. So if I want to get what is the value here, I should multiply by zz into z. So that is this is the z gradient. So that is the field, extra field which is applied. Okay, so this is the extra field which is applied by this field gradient. So and this varies from point to point along the sample. It is here, 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 and it goes from 0 to whatever you choose. This typically, if your main field is like Tesla, right? I mean 10 Tesla. This is of course not that high. This field is something like 50 Gauss per centimeter. 50 Gauss per, that's the kind of a maximum gradient which you use. 50 Gauss per centimeter. That means if you grow along this length of the tube by 1 centimeter, the field changes from 0 to 50. Additional field is applied. The main field plus this additional field. So that is the linear gradient. This is called as the linear gradient. So what is the meaning of that? When you apply the field, the sample here sees the frequency, sees the field differently than here, here, here. Even if it is one line, suppose it is water. Even if it is water. So in the previous case, when the field was homogeneous all through, everywhere, no matter where you are, the absorption frequency of water is the same. It will be at one particular place, one particular frequency. But when you have the gradient, the field is seen by water here, water here, water here, water here, they are all different. Therefore, they will all absorb energy at different frequencies. And that is why it leads to a spread in the frequency of this same signal, of the same water, or any other metabolite, any other signal you might have. So it will lead to a spread in the frequency of this one. This is called as the dephasing. This is the dephasing of the particular signal due to the gradient. Okay, and that can vary. There is typically indicated as delta F. This much variation is there. This will depend upon what is the gradient strength you have, okay, and what is the gamma. The gamma is the gyromagnetic ratio. Therefore, delta is the gradient strength times Z. So because depending upon the Z, you will have a different frequency, different field. Therefore, its frequency is different. Therefore, going from this place to this place, how much is the variation that you will see as delta, because the Z keeps changing. And that is indicated here. As Z keeps changing, the frequency changes here. So the frequency here, 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 they all belong to different points on the Z-axis. Okay. This is called as slice selection. So you can actually use slice selection in this process. A particular slice in your sample has a particular frequency. A different slice will have different frequency. In fact, this is the most important concept in imaging. You can use this slice selection. You encode the frequency in terms of the spatial coordinate. Spatial, because this is Z is the spatial coordinate. As you go along the Z-axis, your spatial coordinate is changing. As you change the spatial coordinate, the field is changing. Therefore, its frequency is changing. So therefore, this is the total width of you have if you have a particular height there in this spot. Okay. Now, in this situation, when you do a free precession, after then, when the presence of the gradient, the single line which is there will now spread out into so many lines. And that is this delta F. Because different portion of the sample gives you different frequency. Therefore, the precessional frequencies are different. So you will have these many different frequencies for the same water, for example, if you're looking at water or any other sample signal you might have. Okay. And when this happens, this will acquire a phase, right? So how much is the phase acquired? So then depending upon how much it has moved, it has acquired a different phase. And that depends upon what is the duration of the gradient. This is called as the gradient duration. So this generate the phase, it will acquire a phase. Overall range of the phase is given by this. 2 pi times delta F times Tg. This is the gradient pulse. For how much duration you apply the gradient. And then for the width of this frequencies will generate a phase accumulation of this type. 2 pi time delta F time delta Tg. This is the phase variation among the various spins. Okay, this is the total phase range which is acquired. This is the dephasing, so to say. Dephasing range, how much it is? This is phi. From here to here, it is, may so call it as phi. Okay. All right. So now you can, so this is schematically indicated here. The transverse magnetization, after you applied, this is the initial magnetization before the gradient, in the absence of the gradient. This is all the magnetization is along one axis, oriented along the y-axis or the x-axis or whatever you might call it. And then when you apply this gradient, ZZK on IZ means it is applied along the Z-axis. So that's basically the operator there. the gradient is applied along the z-axis and gradient strength is this. So and then the different portions of the signals here, ones which are here, this has moved, this has removed there, the next one has moved to this point, third one has moved to this point, fourth one has moved here, here. See, they're all dephased out. In the transverse plane, they have all gone to different positions. That was the same thing was indicated in the previous slide, in only one particular small segment. But here it can spread over the entire plane it can go. So that depends upon the strength of your gradient field. Okay, now you can reverse this. You applied a gradient in one direction. Now you apply the gradient in the reverse direction. When you apply the gradient in the reverse direction, whatever was dephased will now rephase it. Okay, so therefore, if that was the gradient which was going in this direction, field is increasing in this direction earlier, it created a phase difference. Now we can apply a gradient going in the opposite direction. Okay, so therefore that is called as the negative gradient. So when you do that, whatever was created here, it will be annulled by this. Whatever phase difference was created by this gradient, it will be removed by this because it's a refocusing. That's why therefore it is called as the refocusing one. This will depend upon what is the coherence order. Now I'm introducing this concept here, coherence order. We talk about simple magnetizations, which are talking about the single quantum ones, single coherence order. But if I have a double quantum, look at the phase that is acquired. This relationship is important. The minus p gamma I z z z tau. Tau is the time duration of the gradient, and gz is the gradient strength, and z is the coordinate along the x-axis, along the z-axis, and p is the coherence order. So depending upon the coherence order, this coherence would have moved to different extents. Okay, single quantum, if it moves by 90 degrees, the double quantum would have moved by 180 degrees. A triple quantum would have moved by 90 degrees, 270 degrees. Okay, so therefore the coherence order becomes important here. But notice if it is Z magnetization or zero quantum, the gradient does not have any effect on that because the P is zero. For zero quantum, if P is zero, the gradient does not influence the zero quantum coherences at all. And it influences only the single quantum, the double quantums, and the triple quantums. And it also depends upon which direction the phase will increase. Whether it is P is equal to -1 or +1, accordingly, phase acquisition will be in a different direction. It will be a positive phase or a negative phase. So that's because of the P can be +1 or -1. Both this number can be there. So accordingly, they will be dephased out. So now, this is one the phase encoding is indicated here. The phase applied, the gradient applied along one direction, which is the plus ZZ phase. Now in the next one, see the minus ZZ phase. Whatever had dephased here, you remove that by applying the gradient in the opposite direction. So they all have come back along this axis. So this is called as the refocusing by the gradients. This is very important. So you can dephase it by gradients and rephase it by the gradients. So you have to simply change the direction of the gradient. Alternatively, you can also apply a 180-degree pulse in between. Then you don't have to automatically 180 pulse will change the direction. So therefore, you can simply then you can keep the same gradient strength and the direction. So these are the basic concepts with regard to the gradients. How to apply the gradients and what are the consequences of those. So to repeat, when you apply gradient, the field along the z-axis is varied. So it is spatial encoding along the z-axis. So the different points on the sample along the z-axis will have different frequencies. Therefore, they will precess with the different frequencies. So in a given time tau, they will acquire different phases, and that is indicated by these various positions here. And now you can reverse this by applying a reverse gradient, which is minus dz phi. Then you can put them back onto the same plane along the same axis. That is the refocusing by the z gradients. Okay, so these are the important points to remember. Okay, that is again indicated here. Dephasing, so you have the total signal here, dephasing pulse field gradient. So you have created this whole things, and if you look at the net sum of all these, what will be the sum of, what has happened here?
Click on this.
Huh? Where it is not? Okay. So, so they all acquire different phases there. Okay. Now, when they are all over the place in the transverse plane, what will be the total sum of the signal? It will be 0. So when the dephasing has happened, that the magnetization components are spread out all over the plane, then the net of all of these will be 0. Okay. So therefore, you will not get any signal. In the receiver, there will be no signal if you do that. But now if you apply refocusing pulse field gradient, okay, when I say pulse field gradient means the gradient is applied for a short period. And the short periods can be like about 1 millisecond, half a millisecond and things like that. So when you apply that, then this all will come back, then you have the total signal back again. Okay, in some sense, this is like the spin echo. In the spin echo, you are doing the same thing. Initially, after the 90-degree pulse, the signals are dephased out. When you apply the 180-degree pulse, their sign is changed and they rephase after the same tau period. Okay, so therefore they will also refocus. So in the spin echo also the refocusing happens, but that is brought out by the 180-degree pulse. But here you can do by the gradients also. Now you can refocusing pulse field gradient, you will have to have the opposite sign as the field dephasing pulse field gradient if you are not using any 180-degree pulse. But if you use the 180-degree pulse also, then the refocusing pulse field gradient can have the same sign as that, because the 180 pulse has already created a different the negative sign of that. So therefore, the combinations of these are used in practice. Okay, now how do we use this? Selection with pulse field gradients. By applying gradient pulses of different strengths or durations, it is possible to refocus coherences which have, for example, been changed from single to double quantum by a pulse. Coherences of different orders. Okay, before I read this, I want to explain that here. You consider a kind of a running race. Two people are there, A and B. So this is the both are running and somebody has to catch them. Okay, the police has to catch or go to threes or whatever you want to call it. So this is like the phase, this is like the frequency. Okay, this is the speed. The A is running in a particular time, he has moved here up till this point. B has moved up till this point. Now, if you want, if the police has to catch one, he has to reach that place, no? He has to be there. If you want to catch this, he has to be here. If he wants to catch this, he has to be here. Therefore, the receiver phase has to match the phase accumulated. This is like the B is a particular spin which is evolving with a particular frequency. It may be coherence order 1, coherence order 2. It can be different. A may be 1, B may be 2. So they will acquire different phases during their particular time tau, which is the strength of the gradient. So therefore, coherences of different orders acquire different phases during gradients and through the pulse sequence, because you are doing all kinds of things through the pulse sequence. You are applying a 90-degree pulse, various double quantum filter, all sorts of things you are doing. You are creating various orders and the phases keep getting accumulated through the pulse sequence. The receiver phase has to match the phase of the desired coherence. This is what I indicated here. If the police has to catch B, then he has to be there at the point where he has reached over the same period of time. If he want to catch A, then he has to be here. So therefore, he's like the police is like the receiver phase. The receiver has to be at that point, has to be exactly at that place so that he can actually see the catch them. Or therefore, if the receiver phase is matching with this, he will select this, he will collect this one. If the receiver phase is matching this, he will collect the B. And he will not be able to collect A. Also, it's important. He will not be able to collect A if it is thing. That is how the selection happens. The desired coherence is selected by appropriately calculating the phase accumulated through the pulse sequence and adjusting the receiver phase to that. Okay, so this is the general principle. Okay, I will show you here a particular example which you already must have discussed it in the water suppression during the thing. Is a pulse sequence called as Watergate. Water suppression through spin echo. Okay, so here also it also uses the gradients. How does this work? Okay, now this is the pulse sequence is simply this. You have a 90x pulse, then you have a 90 minus x, and these bell-shaped ones are the selective pulses. They are applied only on the water. The hard pulses are the square rectangles. Okay, and 90x 90 minus x, 180 hard pulse, 90 minus x, and the same, a particular time, this tau and this period are the same. It's kept the same. And here you apply a gradient. The gradient, Z gradient, you apply Z gradient, you apply Z gradient of the same sign and the same strength. Okay. Now, we kept the carrier on water. Carrier was on water. That means your main spectrometer carrier frequency, you described it earlier, I guess. So when you, that is where you apply the pulse, the radio frequency of the RF which you apply, transmitter frequency offset after the, okay, that will instrumental aspects. I am coming back to them again in the next class. So that is the carrier. The carrier is on water. Okay, you are sitting on the water. So therefore, water is at zero frequency. Therefore, it has no precessional frequency. Water has no precessional frequency. Now, if you look at this, how much flip angle the water sees? Water sees a flip angle of 90 minus x, 180x, 90 minus x, that means 0. There is no pulse on water. Okay. Whereas here at this point, your signals, sample signals, see a pulse of 180 degree, pulse of 180 degree, right? So therefore, there is a distinction made here with regard to what is the effective pulse applied at this point. How does this work? Okay, so 0 pulse on water, 180 pulse on sample signals. How does this help? What does this gradients do? Okay, let's see that here. So you go through this sequence here. This is for the water. Okay, this diagram is for the water. You have the motor magnetization is on the z-axis. You apply a 90x pulse as you apply for everything else. So this is magnetization comes on the y-axis, let us say. Now during the gradient z, this water magnetization dephases. Okay, although it is at zero frequency, because of the gradient, they acquire different frequencies, right? Therefore, there is not one frequency now. So there are multiple frequencies for water. Therefore, they will dephase. Okay, and then when you apply the 90 minus x to that, you are going to put it back onto the z-axis with this phase difference, with the scatter which is there. Along with that, you put it along the z-axis, which means there will be certain components on the xy plane. That's what it means. Okay. Now, when you apply 180 degree x pulse, then the whole thing gets inverted onto the minus z-axis. Okay. Then we do 90 degree minus x, you bring it back onto the y-axis, and then the gradient now dephases it further. It is not a refocusing here. So it is dephasing it further. So therefore, this will go spread out over all the place. In fact, this will spread out. This will get spread out over the entire transverse plane. So this is only shown a small portion of that here. Therefore, water is, this is indicated here on the tube with respect to the sample tube. So water is getting dephased into various positions on in the transverse plane. So water, therefore, when you take the sum total of all of this, there is no signal. When water is completely dephased, there is no signal, right? The other way to look at the same phenomenon is the way to look at it is this way, that you say that you are not applied any pulse on water, 0 degree pulse on water. So therefore, after the first 90 degree pulse, there is no pulse applied on water. Therefore, what do these gradients do? These gradients continue to dephase it. There is no refocusing them. They are both along the same axis. They are both along the same direction. Therefore, they continues to dephase. The water is continuously dephased out. Whereas the 180 degree pulse is seen by the sample signals, therefore they will get refocused. This gradient, whatever dephasing it has created, and that is returned by this second gradient there. So that is for the sample signals here. You take the sample spins, consider the samples two, I just put two arrows there. This is the sample signal, only one particular, there can be two samples, whatever that is. Okay, if the 90 degree x pulse, magnetization has come on the transverse plane. Now, because of the gradient, I am using this to show here in this manner that they get dephased. They get two different frequencies. That's why I put these two colors there. Okay, initially they were all the same color. But now because of this gradient, they get different frequencies. They get two different signals here. And they will move like this, right? And now when you have the 180x pulse, they will move here. Now, during the next gradient, they will continue to move here and come back to this point. So therefore, that is rephasing. The sample spins are refocused. Because if they see the 180-degree pulse, they get refocused here. The water does not see the 180 pulse. Water is effectively 0-degree pulse. Therefore, it does not see any 180 pulse, and therefore that the gradients continue to dephase there. Here, one gradient dephases, the second gradient rephases. So this is how you achieve a selection. So when you do this, water gets suppressed out because it all remains in the transverse plane all over the place. The sum total of that is 0. So you see the experimental example here of this. This is the spectrum of water. This is the spectrum of the sample with water on scale. That means you maximize this so that this is the water maximum. You don't see any signals of your samples at all, of a sample at all, right? Now, then you adjust your scale such that standard spectrum with the phenylalanine on scale, that is the phenylalanine signal is here. So this you adjust your gain such a way that you can actually see the phenylalanine signals here. Of course, the water signal is now huge. It goes like that. So that's why it is looking very big over there. In this screen, it cannot be completely represented. So you see these two signals, they are already there here, but you cannot see them because here you are adjusted the gain in such a way that you are able to see the top of the water signal. Here you want to see the top of these signals. Therefore, the water signal is going up, is going very high. Okay. Now what you do is you do water gate suppression with phenylalanine on scale. So you look at the water signal where it has come. Phenylalanine signals, full signals are seen, and the water is completely suppressed, and also see the noise. The noise level has come down quite substantially. And this is what happens because they were able to achieve the suppression of the water signal by using this water gate signal by gradients. Okay, now we go to a little bit more complex situation that we want to do coherence selection. So far, we looked at the water suppression and how it was able to help us with regard to the enhancement of the signals. Now, coherence selection. Now, let us say we have the particular diagram with regard to the pulse sequence. We consider the effects of this particular pulse, one particular pulse. And we have here two gradients applied. There is one gradient which has a width of tau1 and the other gradient which has a width of tau2. And it has a strength here. One of them has a gradient strength of G1, other one has a strength of G2. Now we remember what is the phase acquired by a particular coherence order. Let us assume that from here to here, there is a coherence P1. And at this point, by all this during the pulse sequence, and what is this point here? Why I take this point? This is because this is the beginning of this one here, the pulse. The pulse, what is the coherence transfer? Okay. So until here, the coherence is of the order P1. From here to here, the coherence is of the order of P1. During that time, of course, it has got dephased because of the tau1 gradient strength. The tau1 dephased. And what is the phase that is acquired by that? The phase acquired by that is given here. S1 is some instrumentation constant. Forget about this. P1, gamma 1, G1, tau1. This is the phase acquired by this particular coherence during this gradient thing. Okay. This is the width of the total phase. Okay. Now, when I apply this pulse, what happens? This coherence is converted into P2. What was the example? The example was in double quantum filtered Cauchy. So you had, after the first two pulses, you have converted the single quantum into double quantum filter, into a double quantum signal. Therefore, the pulse can convert a single quantum into double quantum or Z magnetization into single quantum. All these things can happen, right? Let us assume that this particular pulse here converts this P1 into the coherence order P2. So this point matches here. Okay. Now, during this, as the P2 is evolving, then you apply gradient for a period tau2. Okay. Now, what will be the phase acquired by this P2? The P2 will have the phase S2, P2, gamma 2, G2, tau2. So, P2 will acquire a phase, this one, and P1 will acquire a particular phase. It is something like this. So, suppose you are driving a car. You go to a particular distance. Okay. Then you come up to a certain distance, you go with a certain speed. Okay. Let's call it as a P1 speed. Okay. Then from that particular point, you suddenly accelerate it and make the speed double. So therefore, within the same period of time, next, you carry a double distance, right? So the total distance that is carried forward is what you have to compute. That is the total phase. That is the total phase, the total distance that is covered. So therefore, if you see the total phase of this, whatever is the phase acquired here, and then what is the phase that P2 is acquiring, then you should be able to follow this path. You should be able to follow this path and calculate the total phase, and that should be equal to the receiver phase. Therefore, we say the receiver phase, then if we put phi1 plus phi2 should be equal to 0. The phase that is acquired by this, the total phase that is acquired by this pathway of magnetization transfer, the total phase should be 0. Therefore, we say phi1 plus phi2 should be equal to 0. In other words, this phi1 is equal to, this will be equal to minus that one. When you put P1 is equal to plus 2 and P2 is equal to minus 1. We have said that the coherence order can be of anything, number 1, 0, 2, whatever it can be. Let us say P1 is equal to 2 and P2 is equal to minus 1. This is what happens in the double quantum filtered Cauchy. In the double quantum filtered Cauchy, this pulse you came here up to with the double quantum signal, and this pulse converted that into single quantum signal here. This happens in the double quantum filtered Cauchy. So it comes here with a single quantum. Double quantum filtered cannot be observed, right? So therefore, you can have to convert that into single quantum. So what was double quantum at this point? Convert it into single quantum here. And you choose P2 is equal to minus 1 for specific reasons. So therefore, what happens here? P1 is equal to plus 2, P2 is equal to minus 1. Therefore, what will happen? If tau 1 is equal to tau 2, if both these numbers are the same, then G2 will be equal to 2 times G1. So your gradient strength, if these two pulses are of the same width, then the strength of this has to be twice that of this one. You could also choose, of course, tau 2 should be 2 times tau 1, keeping the gradient strength the same. If you put G1 is equal to G2, then tau 2 should be 2 times tau 1. So this is how you select the coherent transfer pathways. All other pathways which are there, suppose you have the zero quantum here or Z magnetization here, they will not follow this. When you take this calculation here, they will be eliminated automatically. Therefore, gradient-based selection becomes an extremely powerful tool to select or follow the pathway of magnetization in your pulse sequence. This is exactly indicated here. So this is the field gradient and spin echo. So you can do this. So shown here, this is the coherence order 0 means Z magnetization. You go into single quantum coherence here, that is at this point, and then it continues. And now the dephasing happens during this. Of course, that you don't show it here, but it is still single quantum. It remains a single quantum. The dephasing happens there. And this 180-degree pulse inverts this, converts this plus 1 into minus 1. Coherence order gets converted from plus 1 to minus 1. Therefore, that comes here. And during the next period, you put the same gradient you put. This is what I call as the refocusing. The 180-degree pulse has already caused a change in that one. If we did not have the 180 pulse, then this ZZ would have to have an opposite sign. It should have to minus ZZ. Then it will rephase it. So at this point again, then it will rephase at the point here, whatever point you will rephase. So this is how you do field gradient and spin echo. This gradient double quantum filter was already explained here, so maybe we can skip this. Okay. Now the last point I want to show here with regard to the crusher gradients. What are crusher gradients? Now let us assume that you have gone through a big pulse sequence through the density operator calculations you have done, and at certain point you have the density operator consisting of these terms. You have this Hx plus Hy Cz. This is typically what we have in the Cauchy or the inept pulse sequence. In the inept pulse sequence, you will have this sort of a term. Now, I want to select only this part. I don't want this Hx. Earlier, what we did, in order to do that, we phase cycled it. X minus X, Y minus Y. Then we did 0, 0, 0, 2, whatever. So various kinds of numbers we give, right? But we don't have to do that. Here, we can do it in one scan only. In one scan only, we can do all of that. How do I do it? I want to select this term, but I want to do it in one scan only. So what I do here in this term, I apply 90x pulse to the proton, What happens to X? X remains as X. Okay. What happens to this Hy goes to Z. So now this becomes Hz, Cz. Okay. So now this is along the Z axis. Hz, Cz is not influenced by the gradients because this is along the Z axis. So now this is along the transverse plane. Now apply gradient here, a gradient Zz. This will cancel out all of this. It will dephase everything here. Whatever is in the transverse plane, it will get defaced. Okay. And this is called as a crusher. Because whatever, see this, I have shown a simple example of a single quantum here. It could be double quantum, whatever. All transverse coherences, everything that is there. Not along the, whatever is not along the Z axis. And of course, it cannot remove the zero quantum. But remember that it will not remove the zero quantum. Zero quantum gradient have no influence on the zero quantum because remember the formula P gamma Gz tau. So therefore, P is equal to 0, the gradient will not have any effect. So for that, you will have to use different strategies to remove those if you want to. So now, not affected by, this is not affected by the gradients. Now you apply 90x pulse on the carbon. On the carbon, when you apply the pulse, so you get Cy and Hz, right? So in one scan only, you have filtered it out and you got this desired magnetization on the carbon. This, of course, you can further evolve to get Cx during the another refocusing spin echo period. Then you will be able to collect the signals. Okay, and you see these ones are extremely useful and used extensively in various multiples experiments. I show you here one instance here. Lots of Crusher gradients are used. See here, all of these gradients here, these are all Crusher gradients. And where are they used? See here, this is the inept, particular inept sequence. From here, P1, P2, Y. Now you introduce, what is this pi pulse doing? It is creating that HZ, CZ kind of a thing. HZ, NZ here. For example, this is the nitrogen 15 here. It is creating HZ, NZ. Then I apply the gradient here to remove whatever is in the transverse plane. Everything in the transverse plane is removed. So I only retain HZ, NZ there. Then I apply the next pulse here, then it is brought back onto the, it converts that into the nitrogen magnetization. So therefore, you do already, at every step we can do this. Every time you want to do a magnetization transfer, you separate these two pulses, the transfer pulses by a short period and apply a gradient in between. Same thing is done here, for example. See, between from here to here, you want to transfer from magnetization that has come. And this same is from here to here, for example. Same is here, the G3 gradient, and then the next, this pair of pulses. In the normal experiment, these pair of pulses, they were simultaneous, they were shown as simultaneous pulses, one above the other. But here you have slightly separated them to introduce the gradients in between. And these are typical Watergate gradients. These are the Watergate gradients which we already talked about earlier. Okay, so therefore, dephase unwanted coherences in the transverse plane. This is the use of the Crusher gradients. Therefore, in one scan, you can actually employ Crusher gradients at various places and achieve the signal of your choice, retain the signal of your choice in the final deduction. Okay, so I think this is the end. We'll stop here. Yes. Take a break here, sir.
Yeah.
Yeah.
One break, then we'll start. Is this?
which is a,
This coordinates order is same.
as the M or, what is the M or L? Whose values were of two types? No. So beta, these are the spin states. Beta and alpha are the spin states. Beta is equal to +1, alpha is equal to -1, what? Those are the beta is,
Beta is a spin state, no?
alpha beta are spin states. Okay, and coherence order
I think
with regard to the single quantum, double quantum, zero quantum coherences. Transverse magnetization is single quantum coherence. Okay, and zero quantum coherence is P coherence order is equal to 0.
is I think ML his writing is quantum number, magnetic quantum number.
So
And
those are different. Actually, is magnetic quantum number and orbital quantum number you are
confusing.
confusing.
Actually, another initially, so in the books, we're using this M and L.
That is magnetic quantum number, no?
There is magnetic quantum number.
Discuss
With +1, -1, he got.
See, if L is equal to +1, then we can also have M corresponding to that as +1, 0, -1. That thing can have. But that is for the spin 1 system. You have spin 1 system.
It's a basis of the this magnetization.
Yeah, that is from the spin angular momentum.
Yeah.
Spin angular momentum, it is components of that. Magnetic quantum number is the angular momentum. This reflects the component of the magnetization. If you take it on the z-axis, okay, z component of the magnetization is quantized, or z component of the angular momentum. Let's put it that way to be more precise. Z component of the angular momentum is quantized. So if you have angular momentum is represented by the spin I, then your Iz is the Z component of the angular momentum. That will have two I plus 1 values. And therefore, if it is I is equal to 1, it will have 3 values. And that is represented by the quantum number M, which can go from +1, 0, and -1. If I is equal to half, then you will have +half and -half. And if it is 3 by 2, then you will have +3 by 2, half, -half, -3 by 2, and so on and so forth. Okay, so that has to do with the angular momentum and the Z component of the angular momentum. This coherence order has to do with the phase coherence between the spins in the different energy levels. So if these are between the two alpha beta states of the spin half system, then you will have a single quantum coherence. So if it is between alpha beta and beta alpha, then it is a zero quantum coherence. The alpha alpha beta beta, then it is double quantum coherence.
This is the delta M is 0, delta capital M. Between two, na, alpha beta to beta alpha is 0.
Huh,
Alpha to beta beta is 2.
2. Yes.
That is the way it is.
So that is the coherence order.
For transitions, what we consider is only the single quantum.
Oh, I see that. That's what things might be confusing.
Yeah. So
Delta
from this
is
is 1. Yes.
Delta
Plus
is
half to minus half is a single quantum.
right.
Okay, that's the normal in the normal you see.
Yeah,
That's
yeah.
what she got confused.
So I think that is delta M is what, instead of that, is putting something different.
Yes.
So that is the selection rules. Delta M should be +1 or -1.
Yeah.
I think
Okay, so we'll take a break, few minutes. And then,
That's another 5 minutes.
yeah, this lecture is actually quite long. The second one, this may spill over.
she responded.
She responded something?
Yeah.
Okay, sir.
Okay, got it.
Okay.
इसको बंद कर दो
Okay, so now we finished the module 2 topics up till now. And now there were some additional lectures which are there to, essentially they're supposed to be laboratory experiments, hands-on thing on the thing, but however that is not practical in this kind of an online session. So what Dr. Paul wanted to do is to give a sort of a instruction as to sort of simulate the environment of the spectrometer and what all the things which are of practical importance. So we are going back to the spectrometer now. So we will have to see what all the spectrometer components are, what is the instrumentation in the spectrometer, and what are the things which the operator has to do, the user has to do, how to guess the best spectrum, and of course the analysis follows later on. We have been going through the theory of NMR over all the various experiments, but until you actually sit on the spectrometer and do the experiments yourselves, you will not be able to appreciate that. You have to know the various components of the spectrometer. There are basically 3 components of the spectrometer, essentially, because probably this actually slide shows you that. This shows you have here.
Sure.
This is there. So you have the magnet. Yeah, it's here. You have the magnet here. 3 base. You have the component, the console here. Then you have the workstation. Essentially 3 parts of the spectrometer. So this is the modern spectrometer. Of course, in the early days of spectrometers, these were not like this. They were huge and electromagnets and things like that. But we'll not worry about that. This is the current kind of a scenario of what sort of a spectrometer, what does the spectrometer look like? You have a magnet, okay, and then you have the console. Console contains all the hardware, your RF, transmitter, receiver, everything is inside here. Then you actually see on your screen what all the data you are collecting and do the processing. So this is the workstation. This is where the operator will sit and do all of it. Magnet is here, then the sample will have to be put inside here. It will go down and sit on at this point here. Sample is dissolved in a particular solution. Of course, in the case of solid state NMR, it is put in some kind of rotors. That also goes inside here, and there is a special arrangements for the rotors to move at particular angles and things like that. Okay, so now the inside here, of course, there is what is called as the NMR probe in the mag that sits inside, and that is called as the NMR probe. And your sample goes and sits in the middle of that NMR probe. All your coils are around the NMR sample tube, and they are RF coils. Okay, all the electronics actually connects the magnet to the console. Okay, all the power for the application of the RFs, it is all generated here, and it is delivered to the magnet in the probe, in the coils there. Okay, so therefore these are 3 essential components of your NMR spectrometer. Okay, we'll have to try and understand this in more detail. So this is what are the components in the magnet. I already told you this is the magnet, and you have the sample probe which sits in the middle of the magnet, and the sample goes and sits inside this in this probe. Okay, then the console, all of these other components which are there, they all constitute the console. Okay, and the spectrum is of course where you actually monitor it on your screen. This is on your workstation, and these are all essential components of your console. What do they contain? Okay, therefore the magnet, number 1. Then you have what is called as the field frequency lock. So what does your sample contain? Sample contains, let's say you are recording a spectrum in DMSO or CDCl3 or let's say H2O. CDCl3 already has the deuterium. If you do chloroform, you always have to have some kind of amount of deuterium added to your sample. And what is the purpose of that? That is deuterium, either you add 5% D2 or 10% D2 to an H2O sample, or if you're recording the spectrum in chloroform, then you have to add certain amount of CDCl3, or you're recording entirely in DMS in the CDCl3, no problem. But if you're recording a spectrum in DMSO, for example, you'll have to add deuterated DMSO to that. Some amount of deuterium is required. What is that for? That is for what is known as the field frequency lock. So you lock your magnetic field. Your magnetic field is, let us say, 10 Tesla. Okay, certain Tesla. Now there can be all kinds of fluctuations in this magnetic field because of various instabilities in the movements around the magnet. Magnet is a very sensitive thing. There can be some movements around the thing, and that can cause variations in the magnetic field there. Now, you cannot afford that sort of a variation in the magnetic field because how much resolution you want in your spectrum? You want a resolution of 1 in 10 to the power 10. That is the kind of a resolution you want. That means that is the kind of a stability you must have in your magnetic field. Magnetic field should be so stable that if there are two lines which are separated by 1 hertz, you should be able to detect it. 1 hertz in how much? So if you are taking a 500 megahertz spectrometer, then it is 500 into 10 to the power 6. So 5 into 10 to the power 8. So that is the kind of thing. Then therefore you must have a stability of 1 in 10 to the power 9. That much of stability if we have, then only you can separate two lines which are slightly of that difference. Okay, you want to have that sort of a stable magnetic field, and that is achieved by this unit called as the field frequency law. So it has certain kinds of coils which will actually counter any fluctuations that happen here. So if there is a particular direction the field is changing, this will produce a field in the opposite direction to cancel out those changes, and that is known as the field frequency locking. Okay. Now, before you do that, you will have to shim your magnet. Shim your magnet means there is a set of coils. There are sometimes 28 coils, okay, or 10 coils, 12 coils. There are various kinds of magnets, the different kinds of systems there. These are all coils. What do? They actually generate magnetic fields along different directions, along the x-axis or the y-axis or the z-axis. These are on the linear fields. But there can also be higher order contributions. What does that mean? Any function, if you can express it as a polynomial, you can also express your field as a polynomial of different orders. Therefore, there are various kinds of contributions, first order contributions, second order contributions, third order contributions. All of those things will contribute to the instabilities in your magnetic field. So there is the shim systems, these of various types, which will generate different currents, which will compensate for the fluctuations in this or the variations in this, produce a homogeneous magnetic field over a volume of your sample tube. Your sample tube, let's say you are putting a 5 mm sample tube, and your sample height is of the order of, let us say, 5 centimeters or 6 centimeters or something like that. Then over that volume, your magnetic field has to be constant, absolutely constant, to the degree of 1 in 10 to the power 9. So that much of homogeneity is required in your magnetic field. That is generated by this shim system. The shim system consists of coils which will generate magnetic fields along the x-axis or the y-axis or the z-axis or z square, x square minus y square. These are all higher order changes, and they will compensate for the magnetic field. So typically, as I said, you can express your magnetic field as a time in the spatial coordinate as a polynomial. So there are higher orders will also contribute to the magnetic field changes, and therefore there are shim systems which will generate that sort of fields as well. Okay, now this is to get a homogeneous magnetic field. Okay, after you got that magnetic field, then you have this field frequency log to maintain that field constantly throughout your experiment. Therefore, the system will have to be kept log. In order to do that, what frequency do you use? You cannot use your sample frequencies, because sample frequencies are what you want to measure. So you cannot play around with that. Therefore, you add little bit of D2O, and D2O is, so therefore it has a different frequency compared to the proton. The proton frequency, if it is 500 megahertz, this will be at 50 megahertz, or even how much is 1/6 of that. So it is approximately 1/6 of the proton magnetic field. Those will be very far away from there. So, but however, no matter what the frequency is, you can maintain the constancy of that. So you use the deuterium frequency to maintain the constancy of the field. And when that applies, of course, it is applicable to all your frequencies. That is carbon, proton, nitrogen, to everywhere, the field is going to be constant. Therefore, you need deuterium field frequency log. So why it's called field frequency log? Because it senses the change in the field, which will cause a change in the frequency of the deuterium signal. So suppose there is a small change, delta F, in the field. Correspondingly, there is a small change in the frequency of the deuterium frequency, and then the system will apply a current to counter that change in the field and bring the frequency back to the appropriate value. Therefore, that is called as the field frequency log. Okay. So typically one uses for this a the dispersive signal. You remember you have signals of absorptive type and dispersive type. Dispersive type is like this. Okay, this is the center, and as you go along here, this is your space coordinate, frequency coordinate. So if there is at the resonance condition, this has a zero value. Okay, so a small change in the field will cause a shift in this frequency. Therefore, you will start generating a signal. You will get a signal here. Either you get here or here, you will get a signal. Immediately, you know the field has changed. Therefore, the system will apply counter current to bring the field back so that no signal is there again. Because in the dispersive signal which you use, there will be no signal at resonance for the deuterium signal. So therefore, dispersive signal is very sensitive to the variations in the field, and that's why you use the dispersive signal there. You don't use absorptive signal. Okay, so that is the field frequency log. Okay, now after that, we have what is known as the RF transmitter. RF is your radio frequency transmitter. You have to apply the radio frequency field, right? H1 cosine omega t. So where is it generated? That is generated in the RF transmitter. RF transmitter is a kind of a crystal, so which generates very, very well-defined frequencies. Okay, it generates megahertz frequencies. So whatever is the frequency range you want, there are specific crystals which will generate this RF, and that is supplied to this sample on the coil. There is a coil there. The samples when the sample sits, there is a probe. In the probe, there is a coil, and the RF frequency is applied to that coil. Okay. And what is the transmitter controller? The transmitter controller controls the power you apply to the RF. Okay, what is the phase of the RF? What phase you want to apply? And that is also connected to the receiver here. The receiver, whatever RF you apply to the probe, you also apply to the receiver. You see this reference here? Okay, so this is connected to this as well. Therefore, any phase difference here between this and this is what is called as the phase change. I mentioned to you x, y, minus x, minus y. What does that mean? If this is x and there is a 90 degrees phase, then this will be 90 degrees. This is y. So therefore, if it is 0, 90 degrees phase difference, this will be 90 or y. Therefore, if this is x, if this is 0 and if these two phases are same, then we say 0 and 0. Okay. Therefore, whatever the phase here it is, the same phase is applied here, then it becomes a 0 phase. If there is a difference in the phases between these two, then it is a 90 phase. Now, what else you do here? You see your signals which are coming, they are coming in kilohertz range. Whatever RF transmitter is in the megahertz, right? So let us say 500 megahertz, 600 megahertz. This is 10 to the power 8, 10 to the power 8 signal. But you don't measure there. What your actual spectrum is 10 ppm, 20 ppm. How much is that? On a 500 megahertz, 10 ppm is 5000 hertz. Therefore, 5 kilohertz, right? So therefore, what this receiver does is, whatever frequency is applied here is also applied to this, so that signal that comes out from here, this main signal is subtracted from there. So it's over and above 500 megahertz plus minus 10 kilohertz, plus minus 5 kilohertz. So that 500 megahertz is subtracted out here. Okay, therefore what you see only is the 5 kilohertz or the 10 kilohertz. So therefore the receiver and the transmitter are therefore connected in all ways. And transmitter controls the phases of all of these ones, and the RF amplitude, power you apply, when to switch it on, when to switch it off, all of these are controlled by the transmitter. Okay. After you get the signal in the receiver, then it has to be processed. So this processing is done by this data processing. Now you see all of these are digital signal now. So simple that is coming here in this controller and the pulse width. Okay, now you see in this current pulse NMR, Fourier transform NMR spectrometers, you have the pulses which are of the order of 10 microsecond, 10.1 microsecond, 5 microsecond, etc. Right? Who controls that? That is controlled by this. You can design whether you can, how much is the time gap resolution you can have, nanosecond time resolution you can have. So you can have precise control of how much duration of your pulse should be, whether it should be a 90-degree pulse, 180-degree pulse, all that is designed by this transmitter control. Okay, so therefore these are very precise things. And the sample which you collect, of course, when you do Fourier on the FT-NMR spectrometer, the sample which you collect is not analog signal. So you don't use an oscilloscope there. You're collecting the signal in a digitized manner. So therefore, signal that to collect will be in a digitized form. In the earlier days, of course, the signals were seen in the oscilloscope. In the oscilloscope, the signal is seen in the analog fashion. But you don't see that here in the analog fashion. You see that in the digital manner. It has its consequences, we will see. And then when you do data processing includes all kinds of manipulations, including Fourier transformation. And the pulse programmer here gives a sequence of pulses. What pulses to be applied? What is your pulse sequence? You do a pulse sequence, suppose you are doing a spin echo. So you have to apply 90 tau, 180 tau. Where is that design? That is design is done here. So pulse programmer designs these various pulse sequences and accordingly applies the appropriate pulse at the right time. Given the right kind of a time, this pulse is applied. Therefore, this is what is used for designing pulse sequences. The pulse programmer is actually is a program software where you can write your pulse code through your experiment. Okay, and then you have the data processing. The data processing, of course, is the Fourier transformation and all other kinds of manipulations which are there, we will see. Of course, all of these requires the computer. There is, without the computer control, you cannot do any of these ones there precisely. Then you have the spectrum. After all of this, you collect it on the spectrum. The computer controls all of these things as well. Okay, now let's look at a little bit more into the magnet. You may not have seen the inside of the magnet. It is not easy to see the inside of the magnet. It is a superconducting magnet. Superconductivity, I suppose you know about superconductivity. Superconductivity means if you have a current going in a superconducting coil, it will remain forever. It doesn't, because it has no resistance, zero resistance. A superconducting coil has zero resistance. Therefore, it has no dissipation of energy. Energy dissipation is what? I square times R, right? So if I is the current through this, and if there is a resistance R of the coil, then it will generate a heat or the work done, which is like I square R. So therefore, that is how the energy is dissipated. But if R is zero, then there is no energy dissipation. There is no loss of current. Therefore, whatever, if you have a closed circuit coil like this, closed coil like this, then it will remain forever, provided this coil remains in the superconducting stage. Therefore, you have to create a coil which can go into the superconducting stage. Therefore, this requires certain kinds of materials. Niobium tin is one such kind of an alloy. Niobium titanium is another kind of alloy, and that is used to make these coils. And you induce current in this coil, kind of a closed coil, by using what are called as induction procedures. The magnet charging is an important process in itself. Okay, magnet charging, you induce current into this coil by this process of induction. Okay, and therefore you keep on increasing the current, and up to a certain level you can go, and that is determined by what is called as the transition temperature of the, and how much current the particular kind of a coil can take, the material can take. Therefore, superconducting material becomes important to see how much temperature you can go. Now, how to maintain this superconducting stage? Now, all of these materials, they become superconductors at liquid helium temperatures. Therefore, these have to be inserted in a liquid helium tank. So you have this liquid helium tank here. And notice here, you have a bore which remains at room temperature. You have a coaxial cylinders here, and this is the top of the magnet. The top of the magnet, this remains at room temperature. Your sample comes to room temperature, and you can adjust the temperature whatever you want, but it is surrounded by this coaxial tanks, and the inner tank contains helium, and your superconducting wire is contained in that superconducting in this helium tank, and this probe, your sample goes and sits in the middle of this. Okay, you cannot see this coil because this coil is sitting in the magnet. Your sample is sitting outside. You can lift the sample in and out, but the coil cannot be changed. It remains inside here. So this is helium there, and then outside the helium tank there is also a liquid nitrogen tank. Okay, this liquid nitrogen tank, why is it required? Because you have to insulate the system very well. The helium evaporates. It is at the temperature of helium is what? 4.2 degree Kelvin. So to maintain that helium temperature, you have extraordinarily good insulation. So you have one layer of insulation by using liquid nitrogen tank. Outside of the liquid helium tank, you have a liquid nitrogen tank. And outside of that, there is vacuum here. Okay, this space which is present here, this is vacuum chamber. This vacuum is of the order of 10 to the minus 9. Extremely good vacuum, so that no radiation can go. Okay, I mean, no loss of this thing can happen. it can come in or go. So this is extraordinarily good vacuum, and therefore you can retain this liquid helium for a long period of time. Today, after the magnet design has been changing, and today you have this magnet which can sustain helium almost for a year. Okay, but helium is a very expensive thing. So this shows the interior of that one a little bit more. So you have this 52 millimeter bore here. This is where your sample sits. This is at room temperature. Okay, and surrounded by these coils, the center field. These are superconducting coils there. Okay, and then of course, what is the dimensions are given here? There is the liquid nitrogen here. Then there is the compensation coil. There are various shim coils around there. You also have superconducting shim coils, because to adjust the current, adjust the homogeneity of the thing, first level correction is done by the so-called superconducting shim coils. And you have external room temperature shim coils. So you cannot every day use this superconducting shim coil. That is once and for all when the magnet is charged. At that time only you can adjust this. After that is done, what you are providing in the shim system is external to the this magnet system there. So, and you have this one coils outside there. Okay, so these are the general dimensions there, and typically this axial magnetic field goes up to couple of meters. There is an axial magnetic field which will go up to 5 Gauss line and things like that. We have this outside the magnets. Typically they go to about 1 or 2 meters, but today the insulation and the shielding has become so effective that even that is actually quite substantially compensated, and you don't have the fields, stray fields at far away from the magnetic center. So this is about the magnet. Okay, I'm showing you something here. What is the kind of a current and the coil, superconducting coil details? And look at the technology here, superconducting wire. And to generate a magnetic field of, let us say, 20 Tesla, which was there in the, how much current you require? You require current something about 140 to 150 amperes. If that much high current has to be there, how do you get it? A simple coil cannot, it will just get burnt out. It will simply melt out, because that is normal, this one. In the superconducting stage, how to generate that high current, what you do is, the coil is in the form of number of turns. There is a larger number of turns here. So the coil is of that type. Depending upon the number of turns in the coil, the current gets multiplied by the number of turns in the coil. Now, how to increase this number of turns in the coil? What is done therefore is, look at this cross section here. This is a copper tube, okay, copper wire of, let us say, 1 millimeter or 2 millimeter thing, is probably 1 millimeter. Now you draw holes into this, 64 holes into this, through this, okay, through this diameter, holes into this, and they run through the wire, and you insert the superconducting wire into this. So therefore 64 layers of the superconducting wire are going through 1 centimeter of this. Suppose the wire is about 1 centimeter. So 64 centimeters wire you got already from here, because 64 are there. So therefore that increases the length of the wire, the quantum number of turns of the wire in the superconducting wire here. Therefore you can increase the current relatively easily. And this is the high technology. It's not easy to perform at all. In a 1 millimeter diameter, you have to have 64 holes, and each one of them has to go through superconducting wire. And there cannot be breaks in the superconducting wire. You cannot break it because it has to be so thin, and yet it should be continuous. If it is a discontinuity, then it will not be superconducting anymore. The current will not go because the circuit will not be completed. So it has to go continuous. There will be no break in the coil. So this is a very high technology, and that is the kind of superconducting wire you use. So typically, if you were to 20 Tesla magnet, the total length of the superconducting coil wire is approximately a few kilometers. You can't imagine this. Few kilometers of superconducting wire is inside your magnet, and that is achieved by this sort of a situation. You have a copper wire which is actually a sink. So if there is a kind of a why do you need copper wire, you might ask. Can I just do this? But suppose there is a quenching. Suppose the helium is gone, the evaporation. Suddenly there is a quenching. The superconductivity is lost. So then the whole amount of energy has to be dissipated. There is so much energy there, 120, 140 amperes of current, if it is present, so much energy is there. All that energy has to be dissipated. And that is where the copper comes into the picture. It will help dissipating the energy and all the helium will boil off and you will see all over in your magnet room will be all smoke and things like that. Immediately one has to run away from there. That is all because you can become completely breathless. There is so much helium gas will come out and nitrogen also. Okay, so in the new elements in the FTNMR spectrometer, you have precise timing and already mentioned these delays, data processing, data storage, high power transmitter, pulse generator, digitizer. Okay, digitizer is what I mentioned to you that this is the signal is collected in the digitized manner. Then you have various kinds of filters, then the receiver, there's the detector. So these things are special to FTNMR spectrometer. These are not there in the CW spectrometers. Okay, now I just put in back in a few of the theorems of Fourier transform because these are going to be useful. This may be repetitive for you must have already seen this before, but these I put a few of these theorems because these are required for understanding some of the processes that will happen exclusively for FTNMR. So this is okay. These are general definitions here. Complex FW is Hermitian, means F omega is equal to F star minus omega, F star omega is equal to F omega, F minus omega. So we will not spend too much time. This is additive theorem of Fourier transform, but that is if you collect the time domain data first and then keep on adding signal averaging in the time domain and you do Fourier transformation at the end. You don't have to Fourier transform every FID and in the sense that every scan. So you collect the number of scans, 12 scans, 16 scans, 20 scans, whatever scans you collect. After that you Fourier transform. That is effectively equivalent to do Fourier transformation and adding them. So therefore, this is the additive principle which saves a lot of our processing time. For implications in signal averaging, several FIDs can be co-added and Fourier transformed once at the end to get the frequency spectrum. Okay, now this is an important theorem here. This you must remember. Delayed acquisition, suppose you did not start your acquisition at time t is equal to 0. After the 90-degree pulse, typically you must acquire the data immediately. 90-degree pulse, the data is transferred into the x-axis or the y-axis and immediately you should start collecting the data, but you don't do it because you'll have to give some time for the hardware to relax, hardware to recover. So you give a small amount of time, that delta t. So this is typically of the order of few tens of microseconds, sometimes 100 microseconds. And as a consequence of that, how it will reflect in your NMR spectrum. If FW, F omega is your spectrum, then this small delay causes a multiplication by this kind of a phase. It adds a certain phase to the spectrum. See, this is I omega delta t, like I theta. E to the I theta means a certain amount of phase is added to the spectrum of omega. Delta t represents the delay in the start of data acquisition. The frequency domain spectrum is phase modulated by delayed acquisition. Okay, this will have consequences with regard to the phases in the NMR spectra and how to correct those phases and things like that. That's why I put that theorem again there. Area under the FW, area under the curve. From the definition, you will see that e to the I omega t delta t was there. So if t is equal to 0, what you have? This is integral f omega d omega. That is f of 0 in the time domain, f of 0 is equal to the integral of the entire spectrum. Okay, the first data point therefore is very crucial. The first data point, that is at time t is equal to 0, is the integral of the entire spectrum. Okay, the integral of the spectrum is equal to the value of the first point in the FID. In fact, that is what we also use to say whether this is positive or it is negative. It is also reflecting you whether it is a absorptive signal, positive absorptive signal, or a negative absorptive signal. This also we used on this basis. Okay, now this is another important theorem which is called as the convolution theorem. This is the kind of some sort of a manipulation you can do. If you multiply two time domain functions, f of t and g of t, then the Fourier transformation of that is something called the convolution of the two Fourier transforms. Fourier transform of this and the Fourier transform of that. And that is, this convolution is defined in this manner, f of omega prime into g omega minus omega prime dw, d omega prime. This is the definition of convolution, what it is given here. And this is typically used when you do so-called window multiplication. You have an FID, you collect an FID and then you process it, you multiply by exponential function or a sine Bell function or a sine square Bell function, all kinds of multiplications you do to beautify your spectrum, right? And that is the basis of that is here. So when you do this, it will simplify, improve your quality of the spectrum, and this is the theorem which is important for that. Okay, the next important theorem is the so-called digitization. If f of t is sampled and thus can be considered as a series of Dirac delta functions, you're collecting data points, right? FID is collected as data points. You collect a point here, collect a point here, like that. You are collecting data points, right? So therefore, you can write your FID as a sum of these various in this manner. Summation delta t minus n tau f of t. So this is the delta function, okay? F of t, when it is t is equal to nt, then it is 1, otherwise it is 0. So whole set of all the individual data points are covered by this. So this is how you can write the digitized FID. And when you Fourier transform that, what you get a series of spectra and separated by certain 1 by tau. What is this? N is increasing from minus infinity to infinity. It increases, okay? You look at this one here. 1 by tau, f omega minus n by tau. F omega is your full spectrum. F omega is your full spectrum, right? Omega minus n by tau. If n is equal to 1, is omega 1 by tau. So it is separate. You get a whole series of spectra. Separate spectra you get separated by 1 by tau. So that much will be the separation between the individual spectra. So therefore, when you do Fourier transformation of a digitized spectrum, you get a large number of spectra. I will show you that, of course, it will come later. That you will get like this, a multiple spectra. Each one of them is an f of omega. And the separation between them is 1 by tau. So you will get whole series of that. Here it will go on like that. But of course, then you do filtering. You do filtering to pick out only your central portion. Okay, there where the filters become important. Digital filters are there, which will remove all of those extra ones, and you get this. And this becomes important. Why I'm showing you this? This becomes important to understand the folding of the signals. How alias, it's also called aliasing. The folding of the signals happens because of the theorem. If you don't set your offsets properly, if you don't set your spectral widths properly, then your signals will get folded, and that happens because of this. To understand that, you need to understand this theorem. This is a theorem of digitization. Remember, so theorem of digitization tells you that Fourier transformation of the digitized spectrum produces a series of digitized spectra separated by 1 by tau, and the number of them, and they are filtered to pick out the central one. N is equal to 0, you pick that central one, m is f of omega. And there is n is equal to 1 by tau, 2 by tau, and then also go on to the minus side. Minus 1 plus 1 by tau. So both sides it will go. So you will have a whole range of spectra like that. But the filtering is used to pick out the central one. Okay, so this is the FID I already indicated to you. So you get the digitized spectra in this manner. Okay, and then the spectrum also will be a digitized spectrum. Right? When you do Fourier transformation, you get a digitized spectrum. FID is digitized. Therefore, you also get data points in the spectrum. So as many data points are here as are here, but half actually. Because half of them go into the real component, half of them the imaginary part. Whatever the points are here, you will get half of the spectrum in the real thing, and another remaining half you will go into the imaginary. Okay, now some practical aspects of 50 nmr spectra, the pulse excitation. The pulse excitation, so you apply the RF for a short time here, right? This is the pulse. The pulse is applied means you apply the RF for a short time tau. Now, the Fourier transformation of this is this frequency distribution, which is like this. Okay, this is the sinc function. So you have omega naught is your main frequency. This is what you applied. You applied for a short time tau, and then you see where is that tau in the frequency distribution? The tau appears here. This point is 1 by tau. This is the frequency. So suppose your tau is 10 microseconds, then this will be how much? 10 to the power 5. 10 to the power 5 here and 10 to the power 5 here. So 100 kilohertz, 100 kilohertz. Total from here to here will be 200 kilohertz. Of course, they will have different amplitudes. Amplitude here, they are all different, right? So, but when you want to apply 2h1 cosine omega t, you are considering your h1 to be the constant is the same for all the signals. Otherwise, different ones will get excited to different extents. So the excitation will depend upon the power of your RF, and that is proportional to h1 square. h1 square is the power of your RF. So therefore, if all of them will have to be excited similarly, then you must have the same power for all of those. So what do? You pick out a small region here in this area, and that will have a similar power. When you go to certain other ones, the efficiency of excitation will be different if you go further away. That is why you see you cannot excite the entire carbon frequency, carbon range with a simple RF pulse. The 200 ppm range is too wide to be excited by a simple RF pulse. So all of them, they will have, if one particular portion has very high amplitude, other portion will have a smaller amplitude, the excitation efficiency will be small. That's why if you want to excite the carbonyls in your carbon spectrum, you'll have to shift your carrier close to the carbonyl region. Or if you want to excite the aliphatic one, then you should put the carrier in the aliphatic region in the case of carbon. In the proton, it is not a problem because it is only few 10 kilohertz or something like that. In the carbon, it can go to 25 to 30, 40 kilohertz. There, the spectral range cannot be covered in this small region here. So therefore, one has to shift this omega naught itself to that area so that the region of interest, you get a flat power spectrum here in this area. And that is indicated here. So you take a small region here, which is of importance with a uniform power distribution, and therefore your excitation will be uniform all through your spectrum. Okay, now, so as I said, so the carrier frequency is what your RF is. Now, if you are, let us say you are at 500 megahertz somewhere here, but your actual signals are, let us say, about 40 kilohertz away from there. You cannot excite 40 kilohertz from applying a pulse at this point. This is too far away. Your efficiency of excitation will be very low. So therefore, what you need to do? You need to shift this carrier frequency to this region of your interest. And how is this done? This is done by the computer. The console, there is a hardware which will generate a kilohertz RF, and it is superimposed on this megahertz RF so that you get 500 megahertz or whatever plus minus 30-40 kilohertz where you want to shift it, and that is called as the offset. The carrier frequency offset, this is a priori you do not know where to apply this, right? So therefore, how much offset to apply? Therefore, typically when one does not know all of this, you will have to try this out for various offset values. Okay, therefore, for uniform excitation of all the resonances, it is necessary to move the carrier frequency to the region of interest. Okay, this is what is indicated here. You put the carrier frequency in the middle. Of course, you can also put it in the end. Sometimes you may have to put it in the end also. It has particular reasons are there for that, to do that. Okay, phase of the RF, I already talked about it quite substantially, so I think we can skip this. Phase of the FID. Phase of the FID, you have the phase of the FID, magnetization is here. You apply the X pulse, magnetization goes here, minus Y. Okay, now once its magnetization is here, if you put the detector along the Y-axis, so the magnetization has been rotated onto this axis, you get the FID which is looking like this. Okay, it's maximum here. And if you keep your detector along the X-axis, if you keep the detector here, then your FID will look like this. Because it is 90 degrees out of phase with respect to this. Therefore, at this point, the signal is zero. Therefore, it will, as it moves, as the magnetization moves, rotates here, it rotates in this dimension, then you start collecting components here, then it will start from zero and keeps oscillating like this. Therefore, the mx component will behave this way, the my component will behave this way as a function of time. Therefore, the x component is m0 summation sine omega it, all the various frequencies omega I, and here the y component will be m0 summation cosine omega it. So this is the total of all your frequency distributions. Okay, this slide we have already seen before, and just put it there to remind you that if you have an FID which is like this, which f of 0 is greater than 0, it must indicate an absorptive signal. So you get an absorptive signal here. This will indicate you a dispersive signal because f of 0 is 0. Therefore, the signal will have this shape. And here it is f of 0 is minus. Therefore, your signal will have a negative sign like this. So therefore, the first data point is important to determine what sort of a phase you will have in your spectrum. What is the sign of your things in your spectrum? Okay, now comes single channel and quadrature detection. So detection of only one component, mx or my, is called single channel detection. We often talked about we detect the x component, we detect the y component. Suppose we detect only one component, then we call it as a single channel detection. So what is the consequence of that? Suppose I have an FID like this and I have detected the y component. Now I do a cosine Fourier transformation of this. What do I get? Because FID is cosine omega I t. FID is cosine omega I t. Okay, this one is cosine omega I t, and this is equal to half e to the I omega I t plus e to the minus I omega I t, right? So therefore, this is actually a sum of two frequencies, omega I t and minus omega I t. So when you do a real Fourier transformation, I'll get two signals. One at minus omega I, other one is omega I. Although this is artificial of the Fourier transformation. The real frequency is only one. But since I am collecting only one component, it is an artifact of the Fourier transformation that I am collecting. I am getting two signals here. One at omega I and one at minus omega I. Either one may be true. We don't know which one is true, of course. It can either this is true or this is true. When you say minus omega, with respect to what? With respect to what? With respect to your carrier frequency. With respect to the carrier frequency, if it is higher frequency, then it is positive. If it is lower frequency, it is negative. So therefore, when you do a Fourier transform, so therefore, if your carrier frequency is here, with respect to the carrier frequency, you will have minus omega I and plus omega I. Okay. So, however, only one of them will be correct. Okay. Now, if we detect both the mx and the my components, that is called as a quadrature detection. So let us say we did a my component and a Fourier transform as before. So we get these positive things here. Now I also detect the mx component, let us say. So I put the detector along the x-axis. The magnetization is still oriented here along y-axis. But I collected the FID which is like this, sign dependent sign form. Now what it will generate? It will generate two dispersive signals. Two dispersive signals, the sign component it is. The sign Fourier transformation will give you positive, negative. The cosine is e to the I omega t plus I to the minus omega I t, right? And what is sine omega I t? 1 by 2i e to the I omega I t minus e to the minus I omega I t, right? So therefore, you see, if I collect the sine component, the Fourier transformation of that will generate two frequencies again, but now they will have opposite signs. They may be dispersive in nature because it is sine, but then of course I can apply a phase correction to that to make it absorptive. I make a phase correction and do absorptive, and then I get two components, one is negative, other one is positive. Here I got positive and negative. Now if I collect both mx plus my after doing all of this, then what I get? This is gone. So I get only this signal, right? So therefore, this allows discrimination of positive and negative frequencies if you collect both the components. Typically, you can also think of it like this. So if I let us say I have a magnetization, a frequency has moved here. So this will have one component which is here, other component which is here. So this has, let us say, one sign, other one is this, and another signal, suppose it is present, it is here. This component is the same, but the other component is on the other side, right? So if I collect both of these, then these two will cancel. I will get only this. So that is why if I collect both the components, I will get a single cell. It will allow you to discriminate between positive and negative frequencies. Signal digitization and sampling. Oh, I think should we break here?
We will break here. That is fine. I think we can stop it there.
Yeah, this will go for another hour. This will go for another hour.
Yeah.
So next class, please.
See how many more slides are there? You can see.
I think it will be.
I think this is the longest.
Maybe 10 of here.
Yeah, it's just 40 slides.
So maybe 10 of here.
But these are the experimental aspects.
20.
These are another 22 are there. So I think it will go for another class.
Almost 1 hour it will go.
No, it will come. We stop here.
Yeah.
So we will start with single digitization and thing in the next.
Although I have told those things in very briefly, but I think you are
Yes.
getting into more mathematical part, na?
Okay.
It will be better for the current
Yeah.
participants. They'll
Because now they.
But you can tell me what I can skip, you can tell me.
No, no, it's okay.
don't skip, sir. I think they will get a correlation and they will.
You can go a little bit faster. That's why you are able to go a little faster.
Yeah,
They
yeah.
have that idea. That's good.
I think it will give better idea for them
Yes.
to correlate how the things are going.
Yeah.
Any questions to ask them?
Any questions and doubts?
Rishabh?
No question. No question.
Anyone responded? Sometimes they respond. We just write a line.
Right.
Doubt?
I want to say something.
Any doubt? Ask your doubt, yes.
So any artifacts developed during this quadrature detection also
By free cyclops,
Cyclops it removed.
it can remove, yes. Imperfections in the inaccuracies, in the inequalities in the two receivers. See, earlier they used to use two separate receivers, but today they will use one receiver only, this do a phase shift. And so that the hardware inadequacies will not show up.
Right. Yeah, even if you do this 90-degree pulse also if it is not done accurately,
Yeah.
then it will give error everywhere, na?
Yeah,
As
sure.
long as you are doing these all techniques, na,
Absolutely.
will mess up your spec.
It will mess up your spectrum, absolutely.
Disconnect कर दिया ना? I don't think anybody has asked. कोई तो
No response, yeah.
ठीक है. The next class will be on Wednesday, ना?
Yeah. Wednesday.
जल्दी उसका announce कर दीजिए. Sir, the next class will be on Wednesday at 4 o'clock.
Yeah, next,
Yes, you can.
yeah, the next class will be on Wednesday, 4 o'clock, as usual.
I'll continue this.
And we'll continue from where we left today.
Sir, can we do the frequency of 13 CBs instead of BS? No, but then you have to add.
That is 13C, but that is a,
Natural 13C is not possible.
no. Natural 13C is not possible. You can use any nucleus, but provided there is enough abundance there. But if you are measuring carbon 13, then you cannot do. So deuterium is in abundance. Okay, so that is you put what 10% deuterium, and it is far away.
Level samples can be done.
Level samples it can do. If you are measuring proton, then you can also lock on deuterium. But that is requires you have to configure thing to lock the channels with the C13. Currently all the lock channels are connected with the deuterium.
But recently, Heavy Water Board has purchased a machine, na?
Ah.
They are measuring actually deuterium. So,
Then you cannot lock on.
yeah, they are locking in
Carbon.
other nuclei.
Yes,
They
yes.
are probably using the
Yeah.
hydrogen.
They can use hydrogen, fluorine or whatever. If they are measuring deuterium, then of course they have to lock on
So
something.
they specifically wanted to call the deuterium.
Right.
So I think Drupal has designed a probe, special probe for them.
Yeah. Done? Okay, no other question? Can we do the frequency log with certain nucleus? That is. Yeah.
I think he's satisfied. Okay, then we can stop it maybe.